Anyone who's passed 8th grade knows the general solution. It's minus b plus minus root b squared minus 4ac all over 2a. But most people just plug and chug into this formula, completely oblivious to the geometry that ancient mathematicians used to derive it. You know, back in those days, mathematics wasn't written down in equations. It was written with words and pictures. Take, for example, the equation x squared plus 26x equals 27. Ancient mathematicians would think of the x squared term like a literal square with sides of length x. And then 26x, well, that would be a rectangle with one side of length 26 and the other side of length x. And these two areas together add to 27. So how do we figure out what x is? Well, we can take this 26x rectangle and cut it in half. So now I have two 13x rectangles, and I can position them so the new shape I create is almost a square. It's just missing this section down here. But I know the dimensions of this section, it's just 13 by 13. So I can complete the square by adding in a 13 by 13 square. Now, since I've added 13 squared, or 169, to the left-hand side of the equation, I also have to add 169 to the right-hand side of the equation to maintain the equality. So now I have this larger square with sides of length x plus 13, and it is equal to 196. Now, the square root of 196 is 14. So I know that the sides of this square have length 14, which means x is equal to 1. Now, this is a great visual way to solve a quadratic equation, but it isn't complete. I mean, if you look at our original equation, x equals 1 is a solution, but so is negative 27. For thousands of years, mathematicians were oblivious to the negative solutions to their equations because they were dealing with things in the real world, lengths and areas and volumes. I mean, what would it mean to have a square with sides of length negative 27? That just doesn't make any sense. So for those mathematicians, negative numbers didn't exist. You could subtract, that is, find the difference between two positive quantities, but you couldn't have a negative answer or negative coefficients. Mathematicians were so averse to negative numbers that there was no single quadratic equation. Instead, there were 6 different versions arranged so that the coefficients were always positive. The same approach was taken with the cubic. In the 11th century, Persian mathematician Omar Khayyam identified 19 different cubic equations, again keeping all coefficients positive. He found numerical solutions to some of them by considering the intersections of shapes like hyperbolas and circles, but he fell short of his ultimate goal, a general solution to the cubic. He wrote, "Maybe one of those who will come after us will succeed in finding it." 400 years later and 4,000 kilometers away, the solution begins to take shape. Scipione del Ferro is a mathematics professor at the University of Bologna. Sometime around 1510, he finds a method to reliably solve depressed cubics. These are a subset of cubic equations with no x squared term. So what does he do after solving a problem that has stumped mathematicians for millennia? One considered impossible by Leonardo da Vinci's math teacher? He tells no one. See, being a mathematician in the 1500s is hard. Your job is constantly under threat from other mathematicians who can show up at any time and challenge you for your position. You can think of it like a math duel. Each participant submits a set of questions to the other, and the person who solves the most questions correctly gets the job, while the loser suffers public humiliation. As far as Del Ferro knows, no one else in the world can solve the depressed cubic, so by keeping his solution secret, he guarantees his own job security. For nearly 2 decades, Del Ferro keeps his secret. Only on his deathbed in 1526 does he let it slip to his student Antonio Fior. Fior is not as talented a mathematician as his mentor, but he is young and ambitious. And after Del Ferro's death, he boasts about his own mathematical prowess, and specifically his ability to solve the depressed cubic. On February 12, 1535, Fior challenges mathematician Niccolò Fontana Tartaglia, who has recently moved to Fiore's hometown of Venice. Niccolò Fontana is no stranger to adversity. As a kid, his face was cut open by a French soldier, leaving him with a stutter. That's why he's known as Tartaglia, which means stutterer in Italian. Growing up in poverty, Tartaglia is largely self-taught. He claws his way up through Italian society to become a respected mathematician. Now, all of that is at stake. As is the custom, in the challenge, Tartaglia gives a varied assortment of 30 problems to Fiore. Fiore gives 30 problems to Tartaglia, all of which are depressed cubics. Each mathematician has 40 days to solve the 30 problems they've been given. Fiore can't solve a single problem. Tartaglia solves all 30 of Fiore's depressed cubics in just 2 hours. It seems Fiore's boastfulness was his undoing. Before the challenge came, Tartaglia learns of Fiore's claim to have solved the depressed cubic, but he's skeptical. I did not deem him capable of finding such a rule on his own, Tartaglia writes. But word was that a great mathematician had revealed the secret to Fiore, which seems more plausible. So with the knowledge that a solution to the cubic is possible, and with his livelihood on the line, Tartaglia sets about solving the depressed cubic himself. To do it, he extends the idea of completing the square into 3 dimensions. Take the equation x cubed plus 9x equals 26. You can think of x cubed as the volume of a cube with sides of length x. And if you add a volume of 9x, you get 26. So just like with completing the square, we need to add onto the cube to increase its volume by 9x. Imagine extending 3 sides of this cube out a distance y, creating a new larger cube with sides of length, call it z. Z is just x plus y. The original cube has been padded out, and we can break up the additional volume into 7 shapes. There are 3 rectangular prisms with dimensions of x by y, and another 3 narrower prisms with dimensions of x by y. Plus, there's a cube with a volume y cubed. Tartaglia rearranges the 6 rectangular prisms into one block. One side has length 3y, the other has a length x plus y, which is z, and the height is x. So the volume of this shape is its base, 3yz, times its height, x. And Tartaglia realizes this volume can perfectly represent the 9x term in the equation if its base is equal to 9. So he sets 3yz equals 9. Putting the cube back together, you find we're missing the one small y cubed block. So we can complete the cube by adding y cubed to both sides of the equation. Now we have z cubed, the complete larger cube, equals 26 plus y cubed. We have 2 equations and 2 unknowns. Solving the first equation for z and substituting into the second, we get y to the 6 plus 26y cubed equals 27. At first glance, it seems like we're now worse off than when we started. The variable is now raised to the power of 6 instead of just 3. However, if you think of y cubed as a new variable, the equation is actually a quadratic, the same quadratic that we solved by completing the square. So we know y cubed equals 1, which means y equals 1. And z equals 3 over y, so z is 3. And since x plus y equals z, x must be equal to 2. Which is indeed a solution to the original equation. And with that, Tartaglia becomes the second human on the planet to solve the depressed cubic. To save himself the work of going through the geometry for each new cubic he encounters, Tartaglia summarizes his method in an algorithm, a set of instructions. He writes this down not as a set of equations like we would today, modern algebraic notation wouldn't exist for another 100 years, but instead as a poem. Tartaglia's victory makes him something of a celebrity. Mathematicians are desperate to learn how he solved the cubic, especially Girolamo Cardano, a polymath based in Milan. As you can guess, Tartaglia will have none of it. He refuses to reveal even a single question from the competition. But Cardano is persistent. He writes a series of letters that alternate between flattery and aggressive attacks. Eventually, with the promise of an introduction to his wealthy benefactor, Cardano manages to lure Tartaglia to Milan. And there, on March 25th, 1539, Tartaglia reveals his method, but only after forcing Cardano to swear a solemn oath not to tell anyone the method, not to publish it, and to write it only in cipher, quote, so that after my death, no one shall be able to understand it. Cardano is delighted and immediately starts playing around with Tartaglia's algorithm. But he has a loftier goal in mind, a solution to the full cubic equation including the x squared term. And amazingly, he discovers it. If you substitute for x minus b over 3a, then all the x squared terms cancel out. This is the way to turn any general cubic equation into a depressed cubic, which can then be solved by Tartaglia's formula. Cardano is so excited to have solved the problem that stumped the best mathematicians for thousands of years, he wants to publish it. Unlike his peers, Cardano has no need to keep the solution a secret. He makes his living not as a mathematician, but as a physician and famous intellectual. For him, the credit is more valuable than the secret. The only problem is the oath he swore to Tartaglia, who won't let him break it. And you might think this would be the end of it, but in 1542, Cardano travels to Bologna, and there he visits a mathematician who just happens to be the son-in-law of one Scipione del Ferro, the man who, on his deathbed, gave the solution to the depressed cubic to Antonio Fiore. Cardano finds this solution in del Ferro's old notebook, which is shared with him during the visit. This solution predates Tartaglia's by decades. So now, as Cardano sees it, he can publish the full solution to the cubic without violating his oath to Tartaglia. 3 years later, Cardano publishes Ars Magna, the Great Art, an updated compendium of mathematics. Written in 5 years, may it last for 500. Cardano writes a chapter with a unique geometric proof for each of the 13 arrangements of the cubic equation. Although he acknowledges the contributions of Tartaglia, del Ferro, and Fiore, Tartaglia is displeased, to say the least. He writes insulting letters to Cardano and CCs a good fraction of the mathematics community. And he has a point. To this day, the general solution to the cubic is often called Cardano's method. But Ars Magna is a phenomenal achievement. It pushes geometrical reasoning to its very breaking point, literally. While Cardano is writing Ars Magna, he comes across some cubic equations that can't easily be solved in the usual way, like x cubed equals 15x plus 4. Plugging this into the algorithm yields a solution that contains the square roots of negative numbers. Cardano asks Tartaglia about the case, but he evades and implies Cardano is just not clever enough to use his formula properly. The reality is, Tartaglia has no idea what to do either. Cardano walks back through the geometric derivation of a similar problem to see exactly what goes wrong. While the 3D cube slicing and rearrangement works just fine, the final quadratic completing the square step leads to a geometric paradox. Cardano finds part of a square that must have an area of 30, but also sides of length 5. Since the full square has an area of 25, to complete the square, Cardano has to somehow add negative area. That is where the square roots of negatives come from, the idea of negative area.